So today we are going to talk about low power WANs. This is a new category of protocols being developed, and both of the protocols that we'll talk about today are very new. I mean, basically, I think this is probably the first any university lecture that on these. So first we define, actually I'm going to define low power WANs later on, but basically the idea is right now if you want to go long distance, the only option is cellular phone, and cellular phones are not low power, not good enough for sensors. They are good enough for phones but not good enough for sensors. Phones cost $500 and so sensors cost $5. So anyway, so that is the category. You want to go long distance and a low power. So this chart which you have seen before shows all the protocols that are being developed, and there are such too many protocols being developed right now for IoT, and this probably is the last one. So we will talk about these two which are really common. I have seen, I mean, in some sense I'll show you why they are important, and then rest will be left, I suppose, for future generations. So 11AH, this is also called Wi-Fi Halo, alright, and so this is just on the horizon in the sense that this is a standard which has not yet come out of IEEE, and so there are no products, but it is just on the horizon in the sense that I have the version of the draft 5, which draft 6 will probably become the final version and come out in few months. Once it comes out, there will be a lot of products. Generally, we have seen the same thing in 60 gigahertz, that the wireless HD was the leading technology 3 years ago, but it is no longer there today once 11AD came out, right? So based upon that experience, I feel that 11AH has a good chance. Although if it doesn't come out within a year, then it has no chance because LoRaWAN is taking over the world. Okay, but LoRaWAN is right now the leading WAN. Alright, so we'll talk about LoRaWAN for that reason, and we'll talk about 11AH because this looks like the future. Okay, so it is IEEE spec for low rate, long range IoT applications, and it is currently in the second sponsor ballot. So basically, in IEEE, when some things are done, then it goes through the external people, sponsors. So I am one of the members in the sponsor ballot actually. It turns out so it goes to the external people and they vote upon it. If some comments come back, those comments have to resolve, a new ballot has to be done, and so it keeps recirculating until everybody is happy with it. So right now it is the second round. First round passed with some comments, second round. Maybe second after this round, maybe it will be done. So this is the situation right now. And so what is different about this Wi-Fi is that it is not in 2.4 or 5.8 gigahertz. It is in 900 band, as we call it, sub gigahertz. Sub means below gigahertz, below 1 gigahertz. And below 1 gigahertz, there are two bands, 700, so that this doesn't run in 700. 700 is reserved for something else, which we didn't talk about, that is called white spaces. But this runs in 900 megahertz in the United States, and every country has different. So Europe has 868, Japan has 916, China has 755, Korea has 913, and so that basically causes a lot of problem because you have to make sure that it runs in all of these bands, and every country has a different kind of rules, and this applies to both LoRaWAN and this one. But being sub gigahertz, it has some advantages. I think we had talked about it. I forget when we talked about what, but basically when we talked about some places, we talked about that the lower the frequency, the farther you can go, right? Mm-hmm. And so if we are looking for long distance, we have to look for the lower frequencies, right? And so range is longer than 2.4 gigahertz. Second thing is less congestion, obviously. I mean, there are not that many things that run at 900 megahertz. And better penetration, simply because the wavelength, it can get into the building much easier than 2.4 or 60 gigahertz cannot even get into the building, right? Higher the frequency, penetration goes down. So that way it is a good frequency. And for IoT, it has a low bit rate by design, because if you have a high bit rate, your distance comes down again. So this is more optimized for distance. Short data transmission, so we are not sending large packets. Power savings is most important, and MAC efficiency, so the number of bits that we can reduce is more important. And the number of devices that we can support is very important, so 4 times more devices than Wi-Fi. So basically, this standard, as I present you some of the ideas, you will notice that these are some of the latest ideas for these things. First of all, how to optimize for power savings, how to optimize for short transmissions, how to optimize for low bit rate, and how to optimize for large number of devices. That's what we are learning. Even if 11AH doesn't come through, the next protocol that you will be designing in your own lifetime, will build upon these. Okay, and this uses everything else that we know so far, because this is the latest, plus some new things. So in terms of, this chart is very straightforward. All it says is that you go down the frequency from 60 gigahertz to 5 gigahertz to 2.4 gigahertz, 900 to 700. The range goes up. Okay. So I should have put an additional number here as to what the range is. But you see, this is like a 5 gigahertz is more like a area of a home. It doesn't go all the way home to the home, 5 megahertz. Okay, and BGN goes to the home, so it is like more like 30 meters. If you really want, if a large home, then you really want to run on B. Then AH is what we call neighborhood, so like 1 mile. So if you put it on a post, the whole neighborhood is covered. You can read all the meters in the houses, from a mile away. And this is 11AF could be almost like 40 miles. So basically the 700 megahertz is the band in which the televisions used to run. So previously when you had a television and you didn't need any cable, you put an antenna on the top of your house, the television station could be 45 miles away and you had no problem. Right, with external antenna. So that is what the band is. Basically we took it away from the televisions and gave it to Wi-Fi. I gave it to actually many applications that, we didn't go to white spaces, but that is what is called white spaces. White spaces. So that would have been better than 900, but 900 is what is being used right now for all the IoT devices, because 700 has certain restrictions as to how you use it, for what you use it, and so on and so forth. So, all right. So for 11AH, you can get 150 kilobits to 78 megabits. The maximum you can get is 78 megabits with 4 streams. 4 streams means you have antennas, at least 2 on this side, 2 on the other side. That will make it 4 stream, or you have 4 antennas on this side, 1 on the other side. So with MIMO, you can get multiple streams. So with 4 streams, you can get to 78 megabits per second. Most devices will probably not have 4 streams, so they will be closer to 150 kilobits. And actually what they need is more like 1 or 2 kilobits. So they don't really need much, because they need to send something and then sleep for a day. Then they need to send something and they sleep for a day. By the time you have taken the average rate is not that much. Any questions so far? Sample application is neighborhood area network, NAN. And so you have many houses which have gas meters, water meters, power meters, etc., etc. They can all be read by the access point. And they can have other automation devices that automate other operations of the city. And then you could have sensors through this gateway, basically, which translates 15.4G to 11AH. And then you will send it to the data aggregator through a wired network. So this is where the data will end up, maybe in a cloud. So one new word that you heard, at least 2 on this slide, HAN and NAN. HAN is the home area network. NAN is the neighborhood area network. So what is done for the physical layer? How is it made? How did they get some of the features, and why did they do these features, right? So first of all, they didn't want to invent anything new. So they took 11AC and took the same design except clocked it down by 10. What that means is, instead of 20 megahertz, they will use just 2 megahertz. Instead of 40 megahertz, they will use 4 megahertz. And use the same number of carriers. So 20 megahertz AC uses 64 FFT size and 48 data subcarriers. Right? In AH, they are using the same number of FFT size and same carrier size, but only in 2 megahertz. Things are closer together. Okay? Now, when you put things closer together, there are two things happen. First of all, the carriers are very close, so there could be inter-carrier interference. Right? That's why you don't want to put too close. But there is the opposite effect too, and that is that the time, duration of the symbol, remember T, the FFT T is 1 upon F. If you remember, those of you at least who took the second exam probably remember it much better than who didn't. So 1 upon T, so symbol duration is large. 10 times basically. If the symbol duration is large, that means now you can have 10 times more multipath things that you can sustain. So basically it can go longer distances. So this is basically the reason that they kept the same carrier, number of carriers, so that they can sustain longer multipath interference. And all the time values are 10 times longer basically because of that. CIFS is 10 times longer. CIFS is remote short interframe spacing in 11. ACKs, now there are two things. The time before the ACK is 10 times longer. The ACK themselves are actually 0 length, as you will see in a minute. So the ACK comes 10 times longer after the packet is done. So CIFS it used to come as a CIF. Right? Now CIF itself has become 10 times, so the ACK will come later, but the length of the ACK has been compressed, as you will see, to 0 length. Alright, so now you see the reason for the first decision. First decision is that 11AH is same as 11AC downclocked by factor of 10. Does that make sense as to how it is downclocked? Time is become 10 times longer in every respect. That's why it's downclocked by factor of 10. Yeah.
You said that the symbol duration and time domain will be
10 times.
Yeah, 10 times more. So it makes the intersymbol what?
Less.
Less?
Yeah, see what happens is, what we do is 1/4 of the symbol is reserved for, we used to call that some kind of gap, in symbol gap, cyclic, that is cyclic prefix. So what we do is, now we have a bigger cyclic prefix, and that cyclic prefix allows you to how much, how many different paths you can take. If one path is straight and one path is going through a mountain there, it will come much later. So that delay is spread. Now with
but the data is really low.
That's what we want. Okay. See, the thing is, so that is the second effect, is that data rate is low. We don't want, remember, AC was running at gigabits. We don't want anything in gigas. We don't want anything in megas. We want everything in kilos. We are going in the wrong direction, right? I mean, in this case, we are going in, if you want to call it, in the direction of low rate. Good? Alright. Second thing is, everything else is as before. So now the thing is, some of these are things in the standard. We don't know how much of these will be in the products. So bonding, channel bonding was another thing that was there in 11AC. You remember 20, 40, 80, 160 gigahertz channel bonding. And so they have put here also, instead of doing all possible channel bonding, they said you can just bond maximum 2 channels next to each other. So you can do 1 + 1 to make 2 megahertz. And 1 megahertz actually is a new 5, which is coming up in the 0.5 later on. So all stations have to support 1 and 2. Now 2 is already defined as 20 megahertz. 2 megahertz is the same as 20 megahertz before. But then there is a new one for 1 megahertz. All stations have to support 1 and 2. So this is the minimum. If some stations are not big enough, they don't have too much money, too much power, they don't have to use 4, 6, and 8. 4, 8, and 16. Up to 4 spatial stream, again this is an option. Many stations will not implement that. And 1 megahertz is allowed a new MCS 10, which is MCS 0 with 2x repetition. Now what is MCS? MCS is modulation and coding scheme. That tells you whether I'm using PSK, am I using QAM 64, QAM 16, whatever, right? That is MCS. So every of these modulation is assigned a number. So there is a number from 0 through 9 for different coding schemes. Now they are double using this word MCS 0 for something totally different. And so if you use MCS 10, then it is MCS 0 with 2x repetition. So every bit is repeated twice. So it's like 1/2, one useful bit and 2 bits sent. So all of previous ECCs and everything is there, plus on the top of that, everything is repeated twice. And with that, you can go even much longer. Why? Because now you can sustain even more errors. And if one of the 2 bits is received, you receive the bit. Right? 50% error rate is okay. And so that is MCS 10. And 9 times longer than 2.4. So here is a fair thing to say about this. 9 times is not because of the repetition. First of all, 2.4 and 900 already factor of 3 right there. Right? 900 times 3 would be 2.7. So factor of 3 is already there, right? So the 900 will go without any repetition, without anything, 3 times more. But with this 2x, it goes 9 times. Okay? So again, this decision is made because the distance is important. And the data rate is not important. What we did was we cut the data rate to half. Right? We are sending 2 bits and only 1 is used. So we are cutting the data rate to half, but we are reaching the distance longer. And then beamforming to create sectors. So the thing is, you don't have to put our energy in 360 degrees. You can put it into sectors. No big deal there. So many of these things actually just came straight from AC. AC has beamforming, AC has spatial stream, AC has bonding, and everything else. So they just took all of that, but biased them in the direction of low rate, long distance. Any questions about any of these? Yeah.
You said that besides this double repetition, what was the other reason that you said it goes longer?
Longer is because of frequency. Okay. 900 megahertz will go 3 times longer than 2.4. Actually, 2.4 will go 2 times longer than 5.8, right? Actually, I did an experiment at my home yesterday. So I have a dual band router, and I was not using 5 gigahertz, I was using 2.4 gigahertz, and my son complained that, oh, it's too much, we don't get good internet, this and that. So I was looking for as to how to improve the wireless internet in our home. 5.8 to the place where we want the internet to be from the router, which is the other end of the house. 5.8 had minus 70 dB from the same router, and 2.4 had much higher power. Actually, it was like minus 60 dB, 10 dBs more. Okay? So that is the thing, is that 2.4 reaches much farther, and maybe my even neighbor can probably listen to 2.4. Okay? 5.8 they cannot. However, there was another interesting fact, and that was that 2.8, even though it had higher power, had higher interference, which was not showing in that number. And so when I did the data rate measurement, 5.8 was much faster. Okay, with a lower signal, but there is a lower noise. With 2.4, higher signal and higher noise. right? Everything else runs on 2.4. Your phones run on 2.4, everything else runs on 2.4, your microwave runs on 2.4. So 2.4 actually, previously I had not done this combined experiment where you do look at the signal and look at the data rate. So the higher signal does not really mean higher data rate. But anyway, coming back to this point here is that the shorter wavelength go much farther, and you can see it right in your home, right in your department. And actually, so what I have done as a result is at the end of this lecture, there is a lab you have to do. You have to do exactly what I did. So that you become experienced with using the wireless tools. You become a wireless expert if you don't even know how to measure the power, or how to find the power, or how to set up something. It will not be very good. So you have to play with Insider, which some of these guys have played with who are working on the projects and other things. Okay, all right, back to this is done. Phi is done. Mac. So the Mac had several challenges. First challenge was large number of devices. So how many devices? Wi-Fi can support 2000 Macs. Actually, it cannot support 2000. If you put 2000 computers in this room and one access point, I think it will die. But by design, it cannot even address more than 2000. You cannot even ask them that, okay, please tell me what you want. So 2000 is the limit, design limit of 11, rest of the other 11s. So 11 AD, people wanted, except 2000 is too small. We might have sensors with, meters or whatever we want to read, more than 2000. So they need to do some kind of hierarchical identifier, which I will explain in next slides. And second thing is, generally in Wi-Fi we don't use relays, but I think we have seen relays somewhere, and I don't remember where we saw it, but we will see lots of relays when we come to cellular phones. And so what they do, I think we saw in 60 gigahertz relays. But here they will have similar concept. If you cannot reach some neighborhood far away, you can put a relay there, and then it will come to, you will come 2 hops. So that is another trend I had talked about in the last class, that people are not going for mesh. Mesh is an interesting topic for academics. All the academics are publishing a lot of paper on how to do mesh networking because it's a good mathematical problem. But in the real world, it's a very messy problem. Nobody wants to send other people's packet through their battery, using their battery, right? So it doesn't succeed. So anyway, here it is relay, and the relay is not battery operated. Relay could be mains operated, and relay could be connected to whatever. And so its job is to just transfer packets. 2 hops, that's it. Power saving and enhancements. And then of course the power is the main thing. So now they allow everybody to sleep, including the relays and the access points, and sleep much longer. So they don't have to sleep for a second or minutes or hours. They could sleep for days. Okay? So you are not reading your electric meter every minute or every hour or every second, right? You are probably reading every day. So that kind of sleep is allowed. And you just negotiate your target wake-up time, and you say, well, I want to wake up every 3 days. Okay, all right, you got it. And then speed frame exchange. And second thing is, when you wake up, do all your job and go back. So you do a lot of transmission in one attempt, and you can go back to sleep. All right, and I will actually, I think I have other slides and a lot of slides on all of these points, except the relays I don't have, but I think relays is kind of trivial now. So the MAC protocol has 2 versions. One is version 0. If you don't want to use the new version, which is for 900 megahertz, you can use the old A11 whatever, but then you won't get any of these advantages. Many of these advantages, not any. Many of these advantages. You still get the frequency advantage, but you won't get the MAC advantages. So that is version 0. So they added a field, protocol version. 0 is the old one, and 1 is a totally new one, totally incompatible one, totally, so 1 can talk to 1 only. 1 cannot talk to 0. So it's not a upward compatible. Generally when we say upward compatible, which means that the new people can talk to the old people. Okay? New people know both the old and the new, right? But in this case, 1 is not compatible with 0.
And 0 is not with 1?
0 is totally new, 1 is totally new design. So it's like this and that. I mean, basically, there is no comparison, totally different. And hopefully what will happen is that most of these will be just talking one, because if they want to really talk long distance, they don't care for the rest of this stuff. I think the 0 is allowed for another reason. 0 is allowed because in some cases you may want to do the usual stuff that you do with Wi-Fi. That means you want to light up a whole airport, or you want to light up a whole hospital at 900 megahertz. You can do that, and somehow, so there will be 4 band devices or 3 band devices that will still use the old protocol, right? For that possibility, they have left that in, but I think for IoT, 1 is the best, version 1. It has 4 differences. First of all, the headers have been shortened. So if you are going to send small packets, you don't want to have the same old headers which were large, right? So the headers have been shortened. Null data packets. They have 0 length packets now. 0 length means there is no MAC, everything is PHY. And I will have a slide on that as well. They have a speed packet exchange, which means that you can send 5, 10, 20 packets, just bang, 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 and then go to sleep. Okay? And improved channel access, and then your time to get to the channel has been improved in some way, and we'll show you that. So first of all, short MAC header. So the original header actually is here. The original legacy 1111 has 2 byte frame control and 4 addresses, 2 or 3 addresses, and so on and so forth. And that is, I added something. Now let's see, add it again. 4 plus 6, 10, 16, 218, 24 plus 4, 28 bytes. Right? This is the header. The new one is only 2 plus 2 plus 6 plus 2. So that is 12 bytes. And there are 6 additional bytes which are sometimes used. Okay. So you have 12 to 18 compared to 20. How much was it? 28. So first of all, among the 4 things we talked about, short headers. So we notice now that the headers are shorter by 12 to 18 bytes. Then the second thing is the null data packet. So this is a new data packet which has no data field. Okay? Only 5 bits. Actually no MAC field at all. It just has a PHY field. So the PHY header is there. You get some 5 bits and that's the end of it. Right? Null data packet. And so only 5 bits. That is called NDP. ACK frame identifies the modulation code type. So just like they said, MCS 10 means this new coding. There might be MCS 11, which means that this is null data packet. Okay, so they are reusing this word modulation and coding scheme for this purpose, to indicate what you should expect after the header. Nothing. All right. Block ACK is also NDP with another MCS. So there are other kinds of things that are also null. Block ACK. Block ACK means that I want to acknowledge the last 15 packets. That is group ACK, right? Another MCS which says MCS 12, maybe block ACK. Clear to send is another NDP. So when you say RTS, you get a CTS with no MAC. So they are trying to remove the bits as much as possible. Alright, you get the concept of NDP? So they are using MCS field for all of these. Speed frame exchange basically means that you can send data as many times as you want without doing much. So basically you send the data to access point, and you might say in the header that, okay, I need the response to this. If you need the response will come right away. Within 1 SIF, the response will come. And then if this will say that I want the response within immediately, then you can send the response immediately. And if you have more you can send more. So it is not just limited to 2, you could say 3, 4, 5, 6, 7, so on and so forth. Okay? And then same thing happened in both directions. At the end you will get this black arc, which tells you that I got the whole thing, right? Now, so how do you limit this? I mean, can you continue forever? No. So there is a field called TX-op, transmission opportunity. We had seen this field previously in 11E. So if you remember 11E allowed multiple frames to be sent in what we called enhanced DCF, eDCF. You could send multiple, and so there are four queues, each one had a different TX-op. Right? So this is that TX-op. So basically the whole thing is limited, but it is quite long so that you don't have to send 127 byte packet and then wait for another RTS CTS, then another 127 packet, then RTS CTS. That is just too much, right? Because the packets are short, you can send a lot of them in the same TX-op. Alright, this is also called bidirectional transmit. So basically, it's not just in one direction. TX-op does not just apply in one direction, it applies in both directions. Okay? That is another new, is that the total length is TX-op. And then when you want to send something, you don't have to wait, do anything, just within a SIF, you send whatever you want to send, whether it is the ACK or the data or whatever you are asked to send. Yeah.
In the previous slide, what is this block ACK?
Okay, black ACK is this one, the last one. So group ACK. Black ACK means group ACK. So not each data will not be acknowledged. So let's say you send packet number 16 and then 17, 18, 19, 20, whatever, right? So if some packet is missing, let's say 18 didn't make it, then you will not get this ACK. Right? You will have to retransmit the whole thing. But if you get this ACK, that means you got everything.
So did they start to retransmitting or?
Yeah, so basically in all Wi-Fi protocols, they do retransmit actually. In this case, they will retransmit, yeah. If the ACK does not come. If you expect the ACK. The thing is, you may not even expect the ACK. So here I think, a thermometer, for example, electric meter reading, they are going to read every day, and if they don't get the reading through today, not a big deal, right? Thermometer is sending you temperature probably every maybe 5 minutes, and if you don't get one, it's okay. So you may not ask for the ACK. So it's up to the source to decide whether they want the ACK, and the application, yeah, to decide whether you want the ACK. So it is in the packet. There is a field which says please. Actually, the field is coming up later on. But so there is a field which says that I want the ACK, or I want the data, or I want this, that, and I want multi-packet response. So whatever the source, one side says, the other side follows. So the next thing is, there are 3 kinds of stations. Some are called TIM stations. TIM stands for Traffic Indication Map. Now all of this actually is new, and what I'm seeing is that this was all in this traffic indication map. First time I learned about it was in WiMAX. Before WiMAX, I didn't know about it, but now in WiMAX they have a traffic indication map. Basically in WiMAX, and we will talk about that when we come to LTE, there is a map which tells you when you are supposed to listen, when you are supposed to transmit. Right? So the same thing is here. So in the beacon, there is a map which says, number 1, you can transmit in the slot number 13. Number 2, you can slot number 5, so on and so forth. Right? That way, everybody transmits clearly whenever they need to transmit, and there is no contention. Right? So these stations which can do this, they are called TIM stations, Traffic Indication Map stations. They listen to the beacon and transmit accordingly within a restricted access window. So there is a window which is reserved. Restricted access means only if you have permission, you can transmit, right? So during that window, TIM stations can can transmit, and this is called high traffic stations because these guys are sending very high rate. If you are sending low rate, then you have two kinds. One is periodic, so every 5 minutes you are going to do something. Every 1 day you are going to do something. So they are non-TIM, but they are periodic. So they know that they are going to do this every 5 minutes, or they are going to do this every 1 day. So they can specify that, okay, this is my temperature today, and I will see you tomorrow. Right? So they use they do not listen to beacons. They just go to sleep for a whole day, and then they come up. They already told you that they are going to be sleeping for a day, so they will come back next day and then transmit. And so they don't listen to the beacons. And very low traffic. And then there are people who are even less. They don't have a particular time because they're not periodic. They might be event driven or whatever. So they send a poll to the access point and get a transmission opportunity in response. So they say, hey, I want to send something. I want to send something. So they wake up and they say, I want to send something. And when the access point gets it, then they say, okay, all right, now you can speak. So these are unscheduled stations. So three kinds of stations: TIM, non-TIM periodic, and unscheduled. Unscheduled is whenever you wake up, fine. Yeah.
Unscheduled is as well a non-TIM station.
Non-TIM has a periodic thing, so the access point expects, and they actually get a guaranteed window. They get a periodic restricted access window.
No, I mean the very low traffic is also a non-TIM station.
So non-TIM are in two kinds. Again, let me say, periodic and non-periodic. Okay, that's all there is difference. But periodic, you get guarantee. Non-periodic, you don't get a guarantee. You just have to try. Okay? All right. So now we know three kinds of stations. So now we can say how the channel access works. For TIM, each station knows what segments they belong to. So I got to explain what segment. Let me see. Let me skip this slide and go to segments. Sorry, I was not really sure as to when to talk about what. So I think I need segmentation. So let me just explain segmentation first. Since there are going to be 8,000 stations, if I put a map where station number 1 you speak this and this and that, or station number 3 I have a packet for you, station number 4 you can speak, the beacon will become so big. Right? So we don't even have place for 8,000 bits, let alone anything more than a bit for 8,000 stations. So how do we manage 8,000 stations? They wanted to manage 8,000 stations somehow. Okay, 2,000 is too low, 8,000 is good. So they said what we will do is we will divide them into 4 pages of 2,000 each. So you are on page 1, you are on page 2, you are on page 3. So the beacon will come for page 1, you listen to that, and that is just like before, 2,000. And page 2 beacon is for this thing, and page 3 beacon is for this, right? So every station is in a page, which is called a segment. So we divide the whole network into, it's like a big class we have in WashU. We divide them into sections, right? So you are in section 1, section 2, section 3, section 4. And so that is what the pages are, that is what the segments are. Alright? And so there is a separate beacon for each segment. Pradeep? Pradosh. So there is a segment, there is a beacon. So you see here, there is a beacon for segment 1, there is a beacon for segment 2, beacon for segment 3. This one is heard only by people who are in segment 1. And it has a map only for people who are in segment 1. So it tells you, you speak this, you speak at this time, you speak at this time, and I have packet for you. So there are many beacons for each segment, and then there is basically a common beacon which is at the end of everything. So this is called DTIM, delivery TIM. Okay. In this beacon, which segments are pending data and downlink and uplink periods. So basically, this will say that, okay, segment 1 people, be careful, I have something for you. So when your beacon comes, listen for what that is. If it says, no, I have nothing for you, you can sleep, you don't have to listen for beacon. I have nothing for you, and if you don't have anything for me, you're fine. Right? Otherwise, they have to wake up every beacon and listen whether somebody else sent me anything. Right? So the DTIM, delivery TIM, has something about each segment. And then when you go to this segment, then you can listen to it and act accordingly. So let's see if we covered all the points. Announcing all buffered frame in each beacon. An AP segment, the TIM station in segments announces only one segment at a time. And every delivery TIM interval announces which segments have pending data for uplink and downlink. So you see this big period, and then there are 1, 2, 3, 4 segments at most. I could have put one more, 4. But basically that's what it is. Okay. So this is a DTIM beacon. Actually, this is a DTIM beacon, has a beacon also. So DTIM beacon is actually, so there are 4 beacons already. Page 1, page 2. Actually, let's call it page 0, page 1, page 2, page 3.
That page 0 consists all the stations?
No. Page 0 is page 1 actually. I mean, we count from 0 to 3 and not from 1 to 4. Now, there is something different here. So this one is page 0 beacon plus something in dark blue. That field is not there in other beacons. That is called segment count information element. That has that, okay, segment 0 you have something, segment 1 you have something, segment 2 you have something. So this extra field in that beacon. 0 is not all the stations. Yeah.
Because you said that stations will be divided into different pages. So each page will listen to their specific beacon.
Yeah.
But you said about the DTIM?
Yeah, that 0 will listen and everybody else will listen.
Yes. So it goes for all the stations.
Okay, so that way it is correct. It is correct. It is correct. Okay. So, okay, let me say this one. So DTIM goes to all the stations, but it has the map only for segment 0. And it has a segment map for all the segments. Clear? So that has a segment map which is not there in other ones. So you're right actually. What is happening is that if you're lucky to be in segment number 3, unlucky to be in segment number 3, then you have to listen to this and that. Wake up twice. Well, you have to listen to one only basically. If you have something waiting, then you have to listen to both. Right? Segment 0 has to listen to 0 and that's it, done. But most stations, they just wake up on TIM stations. They wake up if they have something to transmit or if there is something waiting for them which they know from the beacon, from their own beacon, but they can know from DTIM whether they have to listen to their own beacon or not. Alright, so let's go back to where we were. Channel access for TIM. Each station knows what segment they belong to. So station wake up every DTIM interval and find out which beacon they should listen to. The beacon has detailed map indicating which station has pending traffic and when stations can connect for access. We have said all this. If the map indicates AP has buffered packets for a station, the station uses DCF to send a PS pole to get the packet. Now, here I am using what DCF. How many people remember DCF, distributed coordination function? 1? I got to take more exams then. Because you forget after the exam. So this was a basic thing in BC, 11, whatever, in the beginning, distributed coordination function, right? And there was a point coordination function, PCF. If you forget PCF, I can forgive you, but DCF is, Everybody should know. So DCF was the distributed coordination function, which consisted of, like some period being reserved, and then after that some period being, available for contention. You send the RTS, you get the CTS, and you can transmit, right? That is DCF. So using that DCF, you tell the AP, okay, I'm ready, I'm awake. Please give me my packet. If you don't wake up, the next beacon will, you can wake up and you don't lose the packet. Right? And you might lose the packet if you don't wake up for a few days because it will run out of time or buffer or timeout or whatever, right? So the way it is that if you find that you have something buffered, you use DCF to poll and to get it. A station has a packet to send. If it has a packet to send, then it listens to the map and uses DCF to send RTS. So in the map, in the traffic indication map, it says, okay, station 3, if you want to send something, here's the time that you can send. At that time, you send the RTS. And now it is not just reserved for you that time. That might be reserved for 2 of these people, or 3 of these people, or 4 of these people. So in that time, you might have some contention, but hopefully they will not. All of them are not want to speaking, may not be speaking. So you will get through. Okay. So what they are doing is that if all 8,000 stations try to contend with a DCF like before there was no reserved period for anybody, right? Everybody has to just see the symbol and then, draw a random number and then check it out, right? Remember that scheme? Here, they are dividing 8,000 into 2,000 first. And in 2,000, they are dividing into small groups. Okay? And then giving the group a particular slot in which they can contend. Right? So now 4 stations contending in a slot is much better than 4,000 stations contending in a slot. Right? So chances of success are much higher. Yeah.
So here again we have using some random numbers to...
No. So the thing is here, that's the part. Is that you know that you're going to do in a slot 1. Now, I don't know whether in the slot 1 is big enough to draw a random number. You have to do it in slot 1. You cannot do it in slot 2. Right? The slots might be very small, so I don't think there is any random number stuff here. Basically.
I mean, at least in the previous scheme that we had, there were no congestion, but in this one, there might be congestion. If, for example, 2 stations want to transmit at that time slot.
Right. So I will have to check this out again, is that if you did it and you did succeed, the next time when you get the same group poll, right, there must be some mechanism to reduce that from 4 to 2. Okay, and how that happens, that part be there, that you have some probability of saying, okay, I didn't succeed, so now I'm going to take a probability of half to try next time. But there is no random time interval in the sense that, so suppose you are given, let's say 4 of you are given slot number 1. And all 4 you tried, all 4 failed. Next time, all of you will try random number between 0 and 1, and so only 2 will try, and 2 will not try. Because you got a 1, right? You got to wait. And the same slot though, you're not going, right? And then if you still conflict, then next time we'll try number between 0 and 4.
So it's waste of time.
I know, but thing is, here is this general rule. For very heavy traffic, reservation works best. For very rare traffic, random works best. True? Right? So if we expected that we are going to send very high, for AC for example, we expect that people are going to send very large files and videos and movies and things like that. There, random may not be the best idea. You make a reservation and you got your reserved seat. This is random and it's still reserved though. Why reserved? Because it's reserved for 4 of you. You don't get 1 reserved seat per person, but you get 1 reserved seat for 4 people, which is good enough. This is the thing. This is very low traffic. We don't expect this to be used 100% of the time. All right? A small number of stations, and suppose if there's nobody wants to use it, generally most of the time, according to this, they expect that you will come and you will transmit and it will be done. So this becomes TDMA. This is like reserved. If reserved for 4 people and they are not really active, you almost get a reserved seat. That is what TDMA is, time division multiple access. Slot number 1 for you, slot number 2 for you, slot number 3 for you. That's the kind of thing. All right. Any question about this access? Response indication deferral. So this is the bit at the end of the packet. At the end of the packet, sorry. No, actually not the end of the packet. At the end of the PHY header. So there is a PHY, physical layer. There are some synchronizing bits and then some information which says that this is MCS 0, 2, 15, 13, whatever. And there is this red field in the PHY header. And that field tells you how long you should expect this thing to happen. Okay? Previously we had a duration field in the MAC header. Right? The duration field told you that, look, I want to send a 15,000 byte packet. So you added everything, RTS, CTS, CIFS, packet, acknowledgement, and then you waited that long. Right? That was what we call virtual carrier sense. Right? NAV was the name field, network allocation vector. NAV was a timer which you set, and then when the timer expires, then you sense the channel again. But there is no NAV anymore. So we have red. And red is not in the MAC, is in the PHY. So red is based upon 2-bit response indicator field. It is 2-bit, just 2 bits. It's not even a byte, 2 bits. And those could be one of these 4 values. 0, 0, 0, 1, 1, 0, 1, 1. I don't really know which one is 0, 0, but let's just say 4. 2 bits can give you 4 possibilities. And so normal response means that you will wait for a ACK after this data. So I am sending this. After this, I am expecting an ACK. So the receiver will wait for one CIF and send me an ACK or a block ACK. So this is how long you should wait after the end of my packet, right? NDP response means after this, I am expecting an NDP, null data packet. So there is CIF and null data packet. Actually, come to think of it, ACK and block ACK are NDP, so I don't know. I mean, like basically, why would I want normal response? Because not ACK and block ACK are both NDP. And no response means that as soon as I'm done. That's it. There is no CIF and there is no ACK. Long response, that after this, I am expecting a lot of things from the other side. That was that speed frame exchange. I send you something and I get 5 packets from you, then I send you something. And so that is the last one. Long response. CIF plus longest transmission time used with speed frame exchange. That speed frame exchange was the picture that we saw before. This is the one, right? Speed frame exchange. All right. Yeah.
I think that the NDP response is like it at this slide after each data, probably. Before the last act.
Yeah.
It must be for the data for the before the act.
Before the act, the last data.
Yeah, I mean all of the data before the act. They must have some like.
Yeah. So here, I mean, let me just say. let me just say this one. There are many NDPs. ACK is not the only NDP.
Yes.
There is RTS, CTS, I mean, RTS is not NDP. CTS is NDP, ACK is NDP, and there are other NDPs. So it is clear that the NDP response is for more than the ACK. Okay? They started out the ACK separately so that there I'm just expecting this acknowledgement, clearly. The sender is saying that please acknowledge it right away. Where other NDPs can go to the second one. The second one says, well, I really am not expecting for the acknowledgement, I'm expecting NDP response. So there might be other NDPs that you might get.
Also, data is sent by 5 bits, so it's kind of like NDP, so it makes sense that even it works for the data as well.
No, data is not sent by 5 bits.
It's not so because you said...
There is no data by 5 bits.
NDP.
Yeah, NDP is null data packet. Null data is 0. I mean, the MAC is 0. Whole MAC, there is no MAC protocol version or frame control, nothing. 0 bits of MAC. Everything is phi. And in the phi, they have this read, 2 bits of read, and MCS, which might be 4 bits, because MCS is 0 through 10, we already saw, might be 11, 12, 13 to 15. So there are few bits in phi. Alright, so back to power and so this is all about the MAC. So just to be clear about this, MAC had 4 enhancements: short headers, null data packets, speed frame exchange, and improved channel access. Now, whether 11A succeeds or not, you will notice that these features will go into all future versions of IoTs. Okay, and these were not there in Bluetooth, these were not there in Zigbee, and so on and so forth. But as the time is advancing, what happens is you come up with new ideas, and the new people will copy those plus some more. All right, so we go into the power and how do we save power? 3 things we do: page segmentation, restricted access window, and the target backup time. Page segmentation I already talked about, is that everybody does not listen to every beacon. We divide into 4 pages, and then you listen to your page. Actually, page is divided into blocks, and the blocks are divided into sub-blocks, and sub-blocks are defined. So there is a big hierarchy here. So what happens is when you get an AID, your AID is 14 bits, your short name is 14 bits, first 2 bits are your page number, next 5 bits are your block number, next 3 bits are sub-block number, and 3 bits are your position index. Basically, so, up to 8 people in a sub-block. So here it is, 8 stations in a sub-block, 64 stations in a block, 2000 stations in a page, and 8000 stations in the whole thing.